Hi, okay, we have some worked examples here for 2019 paper 3. So first of all, let's have a look at question 1, and in part A we're explaining why a tetrafluoromethane molecule has polar bonds but not an overall dipole. Okay, so this question is all about shapes. All right, so that's the sort of link to your memory that you want to form. And if you look at this molecule, it's very similar to methane that you're much more familiar with. And so the bonding is the same as far as number of bonds is concerned. And so you can see straight away that this can be a tetrahedral molecule. Right, so we've got one fluorine, another fluorine, another fluorine, and another fluorine. So that's the tetrahedral shape. So although the fluorines are all going to be delta minus, all right, and the carbon is going to be delta positive. So we do have polar bonds. The tetrahedral shape is a symmetrical shape, so you see all the delta minuses are pointing outwards. All right. Whereas a polar bond, we need to have direction to our polarity. Okay, so it's a 2-mark question, and first mark is going to be saying something about a difference in electronegativity between fluorine and carbon, something like fluorine is more electronegative than carbon, so that explains why it has polar bonds, right? But the second mark is for explaining it doesn't have an overall dipole, and that's about the shape. So you can say that it's symmetrical or it's tetrahedral to get the second mark. I'll let you write that down yourself or see the mark scheme. So moving on to part B. Now we've got water molecules, right? And we're talking about their MR. And straight away you're thinking that MR of water is 18, right? And on average it is, all right? But there'll be a small proportion of molecules which have, instead of hydrogen 1 or protium, they're going to have deuterium, all right? So they're going to have the isotope of hydrogen that is deuterium. And if a water molecule, all right, had oxygen 16, all right, bonded to hydrogen, deuterium, let's call it, and another deuterium, like so, the MR of this molecule, the molecular mass of this molecule would be 20, all right, 16 plus 2 plus 2 is 20. And that would, putting that into words, would get you the 1 mark. There are other ways to get that mark, because of course you could have tritium involved, so tritium is the other isotope of hydrogen, or you could in fact have isotopes of oxygen. But the most common one, and probably the easiest one, is to talk about 2 atoms of deuterium in the water molecule. Okay, so when we're on part C, about partial pressures, this is harking back to the ideal gas topic, and we've got 20% by volume. Okay, so let's not let volume confuse us, because when we're normally thinking about partial pressures, we're thinking about mole fractions, but of course for an ideal gas, volume is proportional to moles. And so what we can say is that the partial pressure of oxygen here is going to be your 0.21, just your 21% expressed as a decimal, times your total pressure, like that, and the answer is 2.1 times 10 to the 4 pascals. And lastly, part D, we've got what mass of carbon dioxide is formed by the complete combustion of 42 meters cubed of propane. So let's just make a bit of space here for our answer. So first thing to look at in the question is complete combustion. All right, so complete combustion means that we're going to get carbon dioxide. Second thing to notice about the question is our units here. We've got meters cubed, right, and we know that 1 mole has a volume of 24 dm cubed. All right, so we're going to have to do a little bit of a conversion there. And we're talking about propane, and so propane is C3, right, and it's ane, so it's C3H, 6 plus 2 is 8. Okay, so our propane is going to get turned into carbon dioxide and water. This is a 3, I should write that better. So each of those carbon atoms is going to turn into a carbon dioxide molecule, so we're going to get 3 moles of carbon dioxide for each mole of propane. Okay, I won't do the rest of the equation. So let's work through it. So we've got volume first. So let's put our volume into dm cubed. So volume is 42. Right, so it's 1000 dm cubed in meters cubed, so it's 42 times 10 to the 3. Let's just leave it at that, dm cubed. Right, and then we want to work out our moles of propane. So that's moles of C3H8 is volume over 24. Right, so if 1 mole is 24, then the number of moles we've got is our volume, which is 42 times 10 to the 3 divided by 24 for 1 mole, and that comes out at 1750. So we've got quite a few moles, 1750 moles, and as we've worked out down here, that means the moles of our carbon dioxide, right, is 3 times that. But the question is asking us for mass. Alright, so our mass of our carbon dioxide. You remember in mass is moles times mR. Moles we just worked out here, so moles is 3 times 1750, and our mR of carbon dioxide is 44. So that gives us the answer of 2.31 times 10 to the 5 grams. Right, and we just check back in the question that our answer should be in grams, and it should, of course. And why is it grams? Because our mR of carbon dioxide is the unit of that is grams per mole. Okay, moving on to part B. Let's read through the question. We've got a reaction which is first order with respect to hydrogen ions, and at a pH of 1, quite acidic. The initial rate is 2.4 times 10 to the minus 3, and we're asked what is the initial rate at a pH of 3. Okay, so let's see what's happening here. We know the reaction rate in the initial conditions, right, and then we're going to dilute it by a factor of 10 to make it pH 2, and then a factor of another 10 to make it pH 3. Right, so we diluted it 100 times. Right, so the concentration is decreasing, so our rate is going to get slower. Right, but first, before we delve into the calculation, let's notice that it's first order and see what that can tell us. Because for first order reactions, our rate concentration graph is a straight line. Okay, so that means rate is directly proportional to concentration. And what we're doing here is we're decreasing our concentration by a factor of 100. Yeah, because our pH has gone from 1 to 3. So that means our rate is going to decrease by a factor of 100. All right, so our initial rate, so at pH 3 rate equals, all right, the rate at pH 1, which was 2.4 times 10 to the minus 3, but we've diluted that by a factor of 100, right? 10 to go from pH 1 to pH 2, another 10 to go from pH 2 to pH 3, right? So and that gives us the answer of 2.4 times 10 to the minus 5. Okay, so quite a lot of thinking in that one little mark. And next in part F, we've got to find out what the number of oxygen atoms is in 4.26 grams of phosphorus oxide. Okay, so the first thing to think about is when you see number of atoms in the same sentence, you're thinking Avogadro's constant, and the equation that comes to mind, right, that should come to mind is number of atoms, right, equals moles times Avogadro constant. Okay, so and we notice that we've got a formula from which we can get an MR, and we have a mass here of phosphorus oxide, right, and so clearly we're going to work out what moles of phosphorus oxide is, and that equation of course is the good old moles equals mass over MR. So all of this writing that I've done up at the top of the question there is all sort of in your head, I think. So now we can plan, the writing of the actual question as you would do on the exam paper, although you don't lose any marks for any of this scribbling, as long as it's not wrong. So what is the number of oxygen atoms? So the first thing, of course, is that we want to calculate is the moles of phosphorus oxide, all right, and that's going to be our mass over MR. The mass from the question is 4.26. MR, we just count up using our periodic table and we get 142. And so that little sum comes out at 0.03. All right. So we notice, from the formula, all right, this bit of the formula here, that we've got 5 oxygen atoms per molecule of phosphorus oxide. All right. So the moles, right? So let's draw a little semicolon there because I'm short of space. So we've got moles of oxygen, right? So oxygen atoms, that is. All right. So I'm not going to put the 2 of oxygen because that would imply gas. So the moles of oxygen atoms is going to be 5 times the moles of phosphorus oxide. All right. And so that is 5 times 0.03. All right. Now we're going to work out the number of atoms. Right. So number of oxygen atoms is going to be the moles, all right, times Avogadro's constant. All right. So that is going to be 5 times 0.03 times 6.02 times 10 to the 23, and that comes out at 9.03 times 10 to the 22. And there you have your 2 marks. Okay, here in question 2 we've got a practical question. So we've got an interesting fact to start with. So benzoic acid is added to some food as a preservative to make a link with the real world. And then straight on to the practical that you're familiar with. So we're going to prepare this acid with these 3 steps. So first of all, we're going to start with an alcohol, phenylmethanol. So we've got our alcohol there, and we're going to make it alkali with this base, and we're going to oxidize it. All right, so we've got an oxidizing agent, which is our usual manganate. Right, and then we're going to reflux it. Okay, so you're familiar with that practical where we take an alcohol and fully oxidize it under reflux all the way to an acid. Right, then you're going to cool it, acidify it, and get the benzoic acid, right, and recrystallize it to get pure benzoic acid. Okay, so I guess it might be useful just to draw out the reaction that's happening. So let's draw our phenylmethanol that we're starting with. Right, so we've got our benzene ring here that is connected to a CH2 and an OH, right? And we're just going to oxidize that. We don't have to do the mechanism, so we're just going to put, and this is not balanced, we're just going to put oxygen in square brackets there and show the oxidized product here, all right, which would be this carbon now has 3 bonds to oxygen instead of just the one. So it's gone through that oxidation there. All right, so that's the normal reflux. However, we're doing it under in alkaline conditions because we added that sodium carbonate. Right, so this molecule is going to be deprotonated at this stage. So let's just draw out the deprotonated benzenoate ion. All right, so that's all right. Let's just put an OH minus in there, and you don't have to write that down if you were doing this for real. This is just to help your thinking, I think. Okay, so now I think now that we've read it thoroughly and done a little bit thinking about what's going on, we can start answering the questions. So part A, step 1, sodium carbonate. Right, so you see sodium carbonate, and first thing you think of is that it's a base. Yeah. And it tells you that it makes the reaction mixture alkaline anyway. And now it wants an ionic equation. All right, so the next thing you're going to think is, well, okay, that's carbonate ions. That's carbonate ions. The sodium ions just being spectator ions. Right, to show that to show how the carbonate ions form alkaline solution in water. Okay, so if it's an alkaline solution, we need hydroxide ions. All right, so we're going to react these carbonate ions with water. I've not got much space here, so I would write it on the right hand side here. So our carbonate ions can react with water, and carbonate being a base is going to rip a hydrogen off one of these water molecules, all right, and become a hydrogen carbonate ion. All right, it's only 1 minus now because it's taken a proton, so it's acted as a Bronsted-Lowry base by accepting a proton from water, which is acting as our Bronsted-Lowry acid. And what's left behind of the water molecule is just a hydroxide ion. And there we have it. That's the simplest version of the ionic equation that gets you the mark. You could also make H2CO3, right, and a water molecule, but let's leave it at the simpler one. The mark scheme shows you the other options you can write down. Okay, so moving on to B, also just 1 mark, right? So explain why the mixture must be acidified so that crystals of benzoic acid appear. Well, just going back and referring to our benzenoate ion that we created, because we did it in alkaline conditions, we don't have benzoic acid yet, all right? So we need to protonate our benzenoate ion, all right, by adding a strong acid to it, all right? So and that was why we added our hydrochloric acid in step 2. All right, so you write that down. I'll let you write that down yourselves, but you're basically saying a nice sentence on you protonate the benzenoate. Benzenoate ion created in the reflux reaction. Okay, so question part C, write the overall equation for the preparation of benzoic acid from phenylmethanol. Well, if we got back up here, we could probably just do it a bit easier. So we've got C6H5. We're given our formula for benzoic acid. So anyway, our alcohol though, our phenylmethanol is C6H5 CH2 OH, right? And we're making benzoic acid C6H5 COOH. But we have got rid of these 2 hydrogens, the ones that were on that carbon there, right? And they turn up as in a water molecule. and that's what we've created, and so that means that we need an extra 2 oxygen atoms, one that ended up in the water and 2 that ended up in the acid, makes 3, right? So we need 3 on the left hand side as well, so that's why one's already in the alcohol, and so that's why we need 2 there. So there's our overall equation for benzoic acid, and then we can do part D. So in calculating the yield, let's just make ourselves a little bit of space here. So I've cut off the bottom of that page there. So percentage yield, let's remind ourselves of the equation. So our percentage yield equals the actual moles of mass divided by the theoretical times 100 to make it a percentage. Okay, so we need to work out actual and theoretical. Let's start off with the theoretical. Right, I prefer working out moles, doing moles over moles instead of mass over mass. So let's do it like that. So our theoretical calculation, we know that we've got a 1-to-1 ratio in our balanced equation, right? And our theoretical calculation is all about the balanced equation. And from the equation here, right, if we look up in step 1, you see you're given the volume, right, and you're given the density. You're given volume and density, right? And notice the units of density, grams per cm cubed, right? So that reminds you of the formula if you're less familiar with the formula. So what we're going to work out is we're going to work out the mass of phenylmethanol, right? So phenylmethanol, because that's what we're given the data for, right? And so you might either remember or work it out from the units of density that mass equals density times volume, right? Density times volume, and the density we're given there is 1.04. So it's 1.04 grams for every cm cubed, and we've got 4 cm cubed, so we must have 4 times that in grams, right? So that works out. Let's not work it out. Let's convert that straight into moles, right? So moles of phenylmethanol still. And moles is mass over mR, of course. All right, our mass we just worked out as 1.04 times 4. The MR worked out in the normal way, comes out to 108. All right, so our moles of phenylmethanol turn out to be 0.0385. All right, and so now we can work out actual. Right, the actual, if we look in step 3, we see that we're, oh, there's one other step I should do. So actual what and theoretical what? Well, it's moles of benzoic acid, right? But you might remember I referred to a 1-to-1 ratio in the balanced equation. So if we've got 0.0385 moles of phenylmethanol, that means we've got the same number of moles of benzoic acid, right? So let's just put that in here. So moles of benzoic acid is 0.0385, whereas what we actually made is 1.59 grams of benzoic acid. So we can work out moles of our benzoic acid actual. All right, using mass over mR again, but this time the mass that we actually made is given as 1.59. All right, and the MR, all right, we're working out the moles of benzoic acid, so the MR of benzoic acid is 122. Right, so that gives us an actual moles of benzoic acid of 0.0130. Right, compared to what we might have produced in perfect conditions of 0.0385. Okay, so that leaves us just to calculate the percentage yield, which is our 0.0130 divided by our 0.0385 times 100. Turns out at 33.8%. You could calculate it with masses as well if you like. They both end up in the same answer because when you've got moles, the MRs just cancel out. So there you have that. Let's move on to the next question. Okay, in this question, it's straight out of your memories of the practical. All right, so you need to describe how the student can recrystallize the impure crystals to obtain pure benzoic acid. All right, so I can't improve on the mark scheme. Let's just look at the mark scheme. It's here. So notice though that you need to remember that it's the minimum quantity of hot water, so that when it cools, you go past your saturation point, and so you need both minimum quantity of hot solvent. It's probably safer to say solvent rather than water because it might not always be water. All right, for the first mark, and you need to say all of, cool, filter, and leave to dry for the second mark. Okay, put that into a nice sentence, and you've got your 2 marks. So here's question 3, and this is a nice question here. It can be done in class with copper oxide, reduced to make copper. Works really well. You get really accurate results. Anyway, in this case, we've got lead oxide. We've got some lead oxide in a little dish in the middle of this test tube, and we'll pass methane over it and heat it so that it can get reduced to lead by reacting with the methane. And you're going to do all these measurements as well. I'll leave you to read them in order, I suspect, to get an empirical formula. Anyway, let's first of all just do the reduction of lead oxide with methane. So if we've got lead oxide, it might be useful just to think about what the oxidation state of lead is here. All right, so it's going to be +3. All right, and so that is going to be reduced. All right, so we can reduce it all the way to 0. All right. Oxidation state of 0, which of course is going to be lead, and we're oxidizing our methane. All right, so the carbon is going to turn into either carbon monoxide or carbon dioxide, or even carbon as it happens, but the easiest way to work this one is carbon monoxide. It doesn't say full reduction, right? So it's not specific about how you get your lead. Okay, so we can choose this one if we want because it's the easiest one. So the lead plus the carbon monoxide, and you're also the hydrogen of the methane is going to turn into water. Right. So there are 3 products, and we just need to balance them. We see we've got 2 leads on the left-hand side, so we'll stick a 2 in there. We've got 4 hydrogens on the left-hand side, so if we stick a 2 in there, and then we just check our oxygen, so we've got 3 on the right and 3 on the left, so that equation there is good. There are others that you can check the mark scheme for, still ending up with lead of an oxidation state of 0. Okay, so part 2. Student uses safety glasses and a lab coat, of course, right? But it wants state with a reason, right? So you're going to have to say 2 things here. One other important safety precaution. So anyway, lead and its compounds are toxic, right? So you're going to that's this state, the danger, and the precaution would be use gloves or fume cupboard. So there's your two things that you have to say to get the marks for that one. Okay, moving on to part 3, which is here. So now we're just reading it through. Students not sure whether all the oxygen had been removed. And remember that we've got some oxide of lead, let's say for now it's Pb2O3, and we're trying to get rid of all that oxygen, right? We're trying to get rid of that all of that oxygen, so we're left with just the lead. And a student wants to be sure that by the end of the experiment it's only lead there and none of it is lead oxide. Right, so it's asking you for 2 modifications that the student should do to the method illustrated here, to ensure that all of the oxygen had been removed. Well, the obvious one is heat to constant mass. All right, so heat to constant mass. All right, that's the one you'll have done in GCSE in Year 12. And once the mass doesn't reduce anymore, that means that all the oxygen's gone already and you're just left with lead. That's quite tedious, of course, in an experiment like this, because you'd have to wait till all your test tube here had cooled down quite a lot before you could put it on the scales. Nevertheless, that would work, and is one of the acceptable answers. One of the other acceptable answers, of which there are several, would be to continue passing methane over the lead oxide, the sort of stuff that's left, after you've stopped heating it. All right. So what happens in this practical is that to lead to an error is that you stop passing the methane gas across it and you stop heating, but the lead, of course, is still hot, and so will react with air that comes into the test tube, or the oxygen in the air that comes into the test tube after you've stopped passing methane gas through there. Right, so you could continue passing methane gas after you've stopped heating it, right, such that it then cools down, and once it's cool, you can stop the methane gas passing over it. And if it's air reacting, if it's air passing over the cold lead, it won't react substantially to create an error. All right, so in order to get the mark, you could just say continue passing methane across, right, the lead until cool. Right, and you could instead do something even better and pass something inert over the hot lead, like nitrogen, but that's quite involved, and so you would just do it with methane instead. Anyway, there's a couple of right answers. If you want to see some more, check the mark scheme out. Okay, so moving on to part 4, we've got to work out the empirical formula, as we thought. So we're going to look at the data table and see that if we compare this one, right, and this one, that's going to give us the mass of lead, right, and if we compare these two, let's say that one and that one, that's going to give us the mass of oxygen. So we have to compare all, and you'd also have to take the mass of the dish off to get the mass. No, that's right, those two will give you the mass of oxygen. Okay, so then we can do our normal empirical formula table. Okay, so let's make a column for lead and a column for oxygen, and then we're going to work out the masses. We just do those sums that we've illustrated there in red and blue. All right, so we get a mass of lead of 3.132. All right, so this is mass, and we get a mass of oxygen of 0.322. Okay, but of course this is chemistry, we need moles, not masses. All right, so the moles are going to be those masses divided by the MRs. The MR of lead is 207.2. All right, so 3.132 divided by 207.2 is 0.015. Right, and dividing our oxygen by 16, it's oxygen atom, so it's divided by 16, not oxygen gas, which would have to divide by 32, of course. All right, so the moles of oxygen comes out at 0.0201. Right, so now we've got a ratio of moles of lead to oxygen, all right, but we now need to put them into whole numbers. So the usual thing is that we divide the smallest one by itself to make it into 1, right? But we have to do the same to both sides. All right, so we do that, and then we get 1 and 1.34. Right, so this turns into 1, of course, and this turns into 1.34. So sometimes we get whole numbers straight away. In this case, we haven't. So we still need to turn this 1 into this 1 and this 1.34 into whole numbers. So the dodgy one is the oxygen, the 1.34. If we double that, then you get 2.68, which is still not a whole number. So if we triple it instead, we get 4. Okay, so if we times 3, it turns into 4. We have to do the same to both sides again, so that turns into 3. So we've got a ratio of 3 to 4, right? So then we can conclude that the empirical formula is Pb3O4. Okay, moving on to part B. We're a bit crammed here, sorry about that. But we've got silicon dioxide and carbon dioxide, which are other oxides of group 4 elements, silicon and carbon being in group 4 as well. So silicon dioxide, major component of sand, melts at this really high melting point, whereas carbon dioxide melts at this really low temperature, so it's a gas at room temperature. Okay, so straight away we think, okay, silicon dioxide, we're quite familiar with that. It's a giant covalent structure, and carbon dioxide we know already, but from this melting point data, which confirms that it's a simple molecule. Okay, so let's write those down. Structure in silicon dioxide. This is giant covalent lattice. Right, because it's solid, it's a lattice. All right, and the structure in solid. Notice they've put an S for solid here. So you of course have to say simple molecular. Right, but because it's a solid, you need to include the word lattice here. Okay, and the explanation, let me just check the question. Explain the difference in melting points. Okay, so of course, the bonds between atoms in silicon dioxide are all covalent. All right, so whereas the bonds between the molecules in carbon dioxide are induced dipoles or London forces, all right, which are very weak. Okay, so that explains the difference. But the thing to be careful with here is that there's 2 marks for this, right? We've got a mark for this and we've got a mark for this, and it's 4 overall. So there's still 2 marks. So you need to say two things to get the remaining two marks. And the first thing is that you qualify the the strong covalent bonds, strong covalent bonds, or the covalent bonds in silicon dioxide, right? Stronger covalent bonds in silicon dioxide compared to, right? I'll just put versus in to save some space, versus the weaker London forces, London forces in carbon dioxide. So more energy required to break these strong covalent bonds. Right, so that's the two things that you need to say. You need to first of all qualify that covalent bonds are stronger than the induced dipoles, intermolecular forces, right, and also say lead on to the fact that that requires more energy, therefore, to break them. There you have it. Okay, moving on to question 4. Here we've got some Dettol, and as we know, that's a disinfectant because it contains the antiseptic chloroxylenol, and we've got a little diagram of chloroxylenol there, and it tells us that it's a weak bronzolaric acid. Remember, bronzolaric definitions being about donating or accepting protons. So, first question, part 1, is systematic name of chloroxylenol. Right, so let's just go through that in case it's less familiar to you. First thing, you look at this molecule and you can see phenol there. All right, so it's going to be something phenol. That's going to be the suffix, the last part of the name. Right, then we can see that we've got 2 methyl groups here. All right, 2 methyl groups here. So we're going to have dimethyl in the name as well. It's going to be a component of the name. Right, and lastly we've got a chloro in there as well. So these two are going to be the prefixes, right, and that's going to be the suffix because that's the priority group. Now we need a bunch of numbers there as well. All right, so let's number this. Let's number with purple. Okay, so this is phenol, right? So this carbon is going to be carbon number 1. And it's symmetrical, so we can go around in any direction. So this is going to be carbon number 2, 3, 4, 5, and 6. Okay, so number-wise, that means that we've got 3, 5 dimethyl, right? So 3, 5 dimethyl, right? And the chlorine is on carbon number 4, so we've got 4 chloro, right? And the last little deduction to make is that C comes before D in our alphabet, so it's going to be 4 chloro, 3, 5 dimethyl, phenol. All right, so I'll just write that out for completeness. All right, 4 chloro, 3, 5 dimethyl, 3, 5 dimethyl, phenol. Now moving on to part 2, predict the number of peaks in a carbon-13 spectrum. All right, so I've scribbled all over that molecule, so let me draw it out again just for completeness. So we've got a couple of methyl groups hanging off there and a chlorine hanging off there. All right, and so you can see a line of symmetry going down through the molecule like that. Right, so if so that means that that of course is a unique carbon environment, but it does mean that this environment and this environment are the same, so we can number those environments number 2, right? And this environment and this environment are the same, so we can number those 3. This environment and this environment are the same, so we can number those 4. All right, and this environment is different to all the others, and so that is number 5. So we've got 5 environments, so we chuck a 5 in here. Okay, moving on to part 3, we need to name the functional group responsible for the acidity, right? And of course the hydroxyl group of the phenol is responsible for the acidity, all right? Normally alcohols, of course, are not acidic, all right, because the anion is not stable enough, right? But in phenol it is, because the right? Negative ion can have its negative charge stabilized by the benzene ring, but that's not part of the question. So we need to say phenol, all right? So you can't just mention the hydroxyl group because it's only acidic when it's attached to a benzene ring, all right? So you specifically need to say phenol, right? And the test for phenol is that by pH in probe or indicator, the pH is going to be less than 7, right? But lots of things have pH less than 7, not just phenol, right? So we need to also state that no reaction with carbonate. No reaction with carbonate, because a normal carboxylic acid is going to react with carbonate, and it will have a pH of less than 7. So to distinguish it from another acid, you need the two statements there. That's why it's 2 marks. Okay, yeah, moving on to part 4. We've got some more stuff to do with this phenol product, chloroxylenol, and we're told its pH, right? We're told it's how much, how concentrated it is, but we've got unusual units, so we're going to have to take care there. But it tells us, you know, all about percentages as concentrations, right? So we've got a bit of clarification that the only acid we need to worry about is the chloroxylenol. It does say that we've got a monobasic acid, right? So that, you remember, is it means that each molecule of acid's only got 1 proton, and it gives us density of Dettol. Okay, first thing to do here is to write the equation using molecular formula. So notice they want a molecular formula. They've specifically requested molecular formula for the acid dissociation, right? So equilibrium sign, making hydrogen ions and your conjugate base. Okay, so the first thing to do then is to work out what our molecular formula of chloroxylenol is, right? So that's it from the previous page. So we need to count up all the carbons, right? So in the benzene ring we've got 6 carbons, and we've got a hydrogen coming off here, right, and a hydrogen coming off here, so we've got 2 hydrogens. Here and here we've got 2 methyl groups, right, so CH3, CH3, and we've also got a chlorine, and we've also got an oxygen, all right, and we've got another hydrogen in our hydroxyl group, this one here. Okay, so let's add that all up. So we've got 6 plus 2 is 8 carbons. We've got 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, 1 chlorine and 1 oxygen. So there's our molecular formula. Like so. As you remember about molecular formulas, it's not a structural formula, it's got the functional groups in it, it's just the numbers of each atom. Alright, but it wants the acid dissociation equation. Alright, so we're just let's write it down here. Okay, so we've got C8H9 ClO, right, and that's going to dissociate. It's going to lose its proton, right, and the anion is going to be just simply C8H8 ClO, and the minus is on the oxygen. Okay, so there we have our equation, this part done. And next we move on to working out what the acid dissociation constant is. Alright, so let's remind ourselves the equation for it. So it's the concentrations of the products. So we've got hydrogen ions times the conjugate phase. So we've got C8H9 CH8ClO minus, concentration of that. I'm just doing this long formula for completeness, right, for a little bit of revision, divided by our reactant concentration, our acid concentration, right? So we got CaH9ClO. Okay, but of course it's a weak acid. It's only a pH 5.14, right? And it's not a buffer situation, so we can use our approximate formula. So that's the hydrogen ion concentration squared divided by C8H9, our acid concentration, ClO, concentration of that. Okay, so the middle bit you didn't realise, you didn't need. I just didn't twig until I'd already written it down. So let's change colour a little bit, and this, what I'm writing in blue, you might not write on your paper. You might just think it. Right. So where are you going to get your hydrogen ion concentration from? Then, well, it's giving you the pH right up here. Right. So that's going to be from the pH. And where are you going to get the acid concentration from? Well, you're going to get it from mainly that bit of data there. All right. So you're 4.80%, etc. Right. And once you've got those two, you just do the sum and you get the answer. Okay, so let's write it out. Go back to writing it out like we might do on an exam paper. So your hydrogen ion concentration, let's do that one first. That's going to be equal to 10 to the minus pH. The pH is 5.14. Right, and that comes out at 7.244. 7.244 times 10 to the minus 6. Okay, so we've got our numerator now. Now let's write down what else we need. We need the concentration of chlorosilanol, C8, right, H9, right, ClO, concentration, all right. So concentrations, it's not immediately obvious, but let's write down what we do know. We know that the formula for concentration equals moles over volume. We don't know how many moles we've got. We just know that we've got a concentration expressed in a percentage. All right, but we do know that there are 4.8 grams in a 100 cm cubed. So we've got mass. Okay, so let's substitute in mass over mR for, let's just write it out just to be double clear. So we can substitute in moles equals mass over mR into this part of the equation. All right, so that is going to be moles equals, so mass over, all right, so we've got that equation now. Just substituting m over mR in for moles. All right. Now, if we I'm just going to write it in blue again. Right. So we're going to assume we have, right, a volume of 100 cm cubed. Right. So if we assume that we've got a volume of 100 cm cubed, which of course is 0.1 dm cubed, right? Because we need to be working in dm cubed in these calculations. If we assume we've got a volume of 100 cm cubed, then that implies that we have 4.8 grams of our chlorosilanol. Okay, so then switching back to red, we can put our mass of 4.8 in there. So we've got 4.8 grams of chlorosilanol, right, in a volume of 0.1 dm cubed, all right, and the mR is 156.5, 156.5, which you won't, you're not given, so you're going to have to count up all the ARs. So they have it, and that comes out at 0.3067. 0.3067. Okay, so now you've got the components of your Ka, and you fit those in. Don't forget to square your hydrogen ion concentration, and that will give you the answer, whatever it is. So let me save myself doing that calculation because it's straightforward. There, hopefully that's helped you there. Fairly tricky calculation.